National Data Archive on Child Abuse and Neglect.
All right, I think I'm going to go ahead and get started. I have a couple of announcements that I want to share with y'all. So, welcome everyone to our last session of the NDA CAN monthly office hours, Learn with NDA CAN series. NDA CAN is the National Data Archive on Child Abuse and Neglect. It's housed at Duke, Cornell, and UCSF, and we are funded by the Children's Bureau. Welcome, everyone. For folks who have been along with us on the series, welcome back. If you're just joining for the last and final session, welcome. Um, I'll kick it over to Frank to start with our last R series. And as always, we'll spend about 30 minutes talking about R, and then for the last 30 minutes or so, we will get into uh, breakout sessions for office hour conversations. As a reminder, we will be recording this session, and all of our recordings are available on our website. You can catch up or reference back to anything we chatted about over the whole series. Um, if you have a question, please put it in the Q&A chat, or type it into the chat, and we will address them live and just to make sure that we have them captured in the recording. And for any Zoom support that you might need, there's information on this slide here to help you troubleshoot any issues you have. And before I kick it over to Frank, I just wanted to give a couple of announcements because this is our last session. I wanted to let folks know that we do have a summer training series that kind of complements the monthly or is in line with the monthly office hours offering. And so the summer training series, it's themed every year and it's a 5 to 6 weeks every summer. And the theme for this summer is the life cycle of an NDA CAN research project. So we will be walking through everything from initially developing a research question and exploring the data to um, conducting analyses, visualizing and finalizing analyses, and presenting information. So all of that information about the summer training series is on our website, and I will put links in the chat to direct y'all to information and registration links. So that's the summer training series. We also have two paper awards that are housed by NDA CAN. If you're part of the uh, listserv, you might have seen an email from Erin McCauley announcing that earlier this week. So we have an outstanding paper award and we have an outstanding graduate student paper award. I will also put information in the chat about what that looks like, and how you can nominate folks for these awards. Those nominations are due by July 15th. And if you have any questions about the summer training series, any of the paper awards, or future NDA CAN offerings, uh, feel free to reach out to me either in the chat or via email. Um, I think that is all of my announcements. So, Frank, I'm going to kick it over to you to get us started.
All right, great. Thank you, Paige, and welcome everybody. Today, we are going to talk about a couple of topics in advanced regression. The materials for this course are the same as always. They're on the Cornell Box folder. So all of the data that we're using today is available for you on Box, along with these slides and the R script that we will take a look at in a moment. So this week, we're going to give a kind of taste of a couple of techniques that we could, ways that we can do advanced modeling within R. This is obviously in 30 minutes, not going to be a complete overview of the, thousands of topics that we could discuss on advanced modeling. But R is a very flexible programming language, and most statistical approaches that you might see in the literature are both implementable in R if you have the patience to program it yourself, but also generally available to you through third-party packages. It's one of the big features of R is that it's an open source project. So third-party developers are routinely expanding the capabilities of the R suite. Today, we're going to talk about two particular topics. We introduced linear regression last time. This time, we're going to talk about how you can estimate generalized linear models in R and also how you can estimate multi-level models in R. The data we'll use today is the AFGARS fake aggregated and the AFGARS fake individual level data, along with some census data. Again, these are simulated data. They are not real foster care data, so please don't use them for research. They are intended only for the kinds of practice that we're doing here, but you can order the full data from NDACAN as usual. And feel free to raise your hand or just go off mute if you have questions as we go. I'm going to start with talking about generalized linear models, and I'm going to assume that most of us have seen these topics before in a statistics course or are familiar with these topics, but I'll just give us a brief introduction and then we'll go into the coding. So a generalized linear model extends the linear regression model, where we define the expected value as a linear function of a set of predictors and a set of parameters, by including a link function g. So what we're going to do here is we're going to apply a link function to the left-hand side of the regression equation to transform the right-hand side of the regression equation into a linear relationship. So it's effectively going to allow us to model nonlinear processes using the same regression tools that we already know how to use. And we can use a wide range of link functions g to accomplish this. But some of the most common ones we'll see are logistic regression, where we use the logit as our link function. And then once we apply a logit to the expected value of y, we can model the relationships between variables in our typical linear format. But this means, of course, that the actual relationship between x1, x2, and the probability of y, because logit models are typically used for binary outcomes, now becomes nonlinear because we are applying this nonlinear transformation. So implicitly, we could imagine applying a logit inverse to both sides, where the expected value of y would now be equal to the logit inverse beta 0 plus beta 1 x1 plus beta 2 x2. Poisson regression is another commonly used GLM, generalized linear model. And with the Poisson model, and along with a number of other models in the exponential family, we're going to use the natural log as our link function. So here's a kind of quick overview of effectively what we're doing with GLMs, right? Under ordinary linear regression, we're saying that our y's center around the regression line, b0 plus beta 1x plus beta 2x plus an error term epsilon, where those error terms, epsilon, follow a normal distribution around the regression line. So we say that our y values will sit along centered on the regression line with a normal distribution around the regression line. Under logistic regression, we're saying that our y's are going to be modeled according to a Bernoulli probability distribution. That is a probability distribution that takes the value, the parameter p, and then generates a random value that has probability p of being equal to 1. And in order to model the process for p, in order to understand why different levels of x values correlate to different probabilities that y equals 1, we will set up this logit inverse linear equation. For Poisson regression, we're going to specify a parameter named lambda that we are going to say is equal to e to the beta 0 plus beta 1 x1 plus beta 2 x2, right? And we know now if we take the natural log of both sides, we could end up with log of lambda is equal to beta 0 plus beta 1 x1 plus beta 2 x2, right? And this is the generalized linear model component of it. We're just transforming our ordinary regression equation using these link functions. And here we're going to say that y follows a Poisson distribution with the parameter lambda, which is going to determine the expected count. So Poisson regression is something we often use for integer count values, non-negative integers. And Poissons take one parameter lambda that defines both its expectation and its variance. Now, how do we do this in R? It's pretty easy. We used LM last time to estimate regression models. The only difference here is we're going to add a G onto LM. So for a logistic regression model, we will specify the model as GLM parentheses y tilde x, and x then can be our full set of predictors, x1 plus x2 plus x3 times x4 if we like. We provide a link to the data that we're using. And now we also need to specify the distributional family that we are saying that our outcome follows. So in this case, the Bernoulli model we mentioned a moment ago is a special case of the binomial distribution with n equals 1. So we're going to use the binomial probability distribution as our family argument. What's the distributional family that y follows? In this case, we're saying it follows a binomial distribution. Under Poisson regression, we'll use the exact same setup, GLM, y tilde x, data equals my data. Now we're going to use the Poisson probability distribution for our family for our outcome variable. Pretty straightforward. We'll go over to RStudio in a moment and look at how we actually estimate and interpret the output of these models. I also want to briefly introduce multi-level models. Again, this is an incredibly rich and complex topic. We could spend an entire semester discussing multi-level models if we wish to, but I want to just give us a quick overview of how they work. We can define a multi-level model with varying intercepts for cluster J as y is equal to beta 0 plus beta 1x plus beta 2x2 plus delta J plus epsilon I. I'm setting up this new term, this new parameter in my regression called delta. And what delta is going to be is it's going to be a set of cluster level intercepts. So we're going to have effectively two error terms in our model. We'll have our epsilon, which indicates individual level error. Let's imagine that what we're modeling here is county level foster care dynamics, and we are modeling those over time. So our observation might be the county year foster care caseload, but we also know that counties, especially in a system like the child welfare system, can vary a lot across, can vary a lot in ways that are stable over time. So features of jurisdictions often change very slowly over time, or demographic features of places often change very slowly over time. What this delta parameter will let us do is it will let us estimate an intercept specific to each county in the data that doesn't change over time, so that we can pull out some of those time stable differences across counties from our inferences about our betas. So it's an incredibly useful feature, incredibly useful tool for addressing various kinds of clustering that we might observe in the data. And with the NDACAN data, a routine kind of clustering that we're going to have to deal with is geographic or spatial clustering. Multi-level models are a really useful tool for that. In R, we're going to use the LME4 package. This is the most commonly used package for estimating multi-level models in R. There are others, but they follow a similar syntax. And we're going to use our standard LM formula with one small twist. So to estimate a linear multi-level model, I use the LMER function. So it's just LM plus the ER. And in this case, MER stands for mixed effects regression. So that's linear mixed effects regression of y tilde x plus, I apologize, our font doesn't have serifs, but that's a 1 and then a bar J. And what that's telling R to do is to estimate a linear regression with an outcome y and predictor x plus a random intercept for each level of the categorical variable J. That 1 bar J says estimate random intercepts for each level of J. Data equals my data. Now, LME4 extends to GLMs, so we can estimate linear multi-level models, or we could estimate generalized linear multi-level models. So we could estimate a multi-level Poisson model if we think there might be clustering. Let's say we want to estimate a multi-level slope and intercept model. We could estimate that model with the outcome Y, the predictor X, with multi-level slopes for the variable I by unit J. So what the model on this bottom row is going to do is it's going to estimate not only an intercept for each level of the cluster J, but it's going to estimate a slope. Let's say I is our time unit here. Now each county in our data, if we stick with our county year kind of toy example, each county will also get, in addition to an intercept, it'll get a slope that's unique to that county over time. Now, these formulas can get really complex, and it's a little confusing when you first get started with it. There's a really great explainer on Stack Overflow on Stack Exchange for LME4. If you just Google search LME4 cheat sheet, you'll get to it pretty quickly. But I've provided a URL to a thread on Stack Exchange that does a pretty good job explaining how this formula setup works. It's very similar to what we've done with the LM function, with this additional syntax for how we specify the random component of the model. All right, so let's go over to RStudio and actually estimate some of these things. All right, so what we're going to do is we're going to pull in our data. We're always going to start with tidyverse. We're going to fix this minor typo, and I apologize, and I realize that I didn't. Do I library in LME4 somewhere? I need to. I'm going to library in LME4 here. So let's just parse our data real quick. I'm going to put my cursor here, and I'm on a Mac. I'm going to hit Command Option B to run all code above line 13. On PC, that's Control Alt B. It's a nice hotkey to use when we want to restart what we're doing. And then I'm going to go to line 15 and hit Command Return to look at the head of AFCARS AG to give us a sense of what's inside of this table. We'll do the same for AFCARS End and the same for census. So that just tells us what's going on. Now, what I'm going to do is I want to join these tables together. We're going to estimate one model using the AFCARS individual level data and another set of models using the AFCARS aggregated. For the AFCARS aggregated, I'm going to want to join it to the census. So I need to do a little bit of cleaning work, and this is the kind of stuff we covered in the first few weeks of our Learn session. You can always go back and check those videos out. But also the Hadley Wickham's Introduction to the Tidyverse book is a stellar book for learning how to work with the kinds of data manipulation tools that I'm showing here. So we are renaming some variables in AFCARS AG, and we're grouping by year and state to basically group to sum over all racial groups in the data to create a total sum of the number of children in our simulated data that both entered and exited foster care. In the census, we're grouping by year and state to sum the total population size for those states by year, and then we're joining those two tables together with AFCARS AG. And let's confirm that that looks right, and it does. So now we have a data set at the state year level where we have entries in column 3, exits in column 4, and the total size of the population in column 5. Looking good to me. Now we're going to go back and look at this AFCARS End again, which is right here. And the first model I want to look at is thinking about the relationship between a set of predictors like sex, race, ethnicity, age at last removal, whether parents were known to be incarcerated, and a neglect allegation on that child's foster care case. So we're going to estimate this as a logistic regression model where neglect is our outcome, and we can see that this is a binary outcome, ones and zeros here. I did have to change how I parsed this. There are some variables that have the label null in the individual file. So I told R in its parsing of the file to treat those nulls as missing values. So you can add this NA equals argument onto your read CSV to tell R how to parse things that you want it to treat as missing. But let's just go ahead and estimate this model real quick. All right, so now we have something called M1 stored in our environment. If we look in our environment tab, we can see it right here. It tells us it's a list, but we have a new object called M1. That's great. We're going to look at it. Summary is an easy way to look at model output in R. And so this will give us our old friend, the linear regression table. Now, you have to be careful with logistic regression models because now we are not, for example, the link function, the logit link function means that our interpretation of these coefficients is wildly different than it was under the linear model. So now what we have, for example, if we look at the age at last rem variable, what we find is that for each year of age that a child has, their log odds of having a neglect allegation on their case are 0.06 lower. What this is telling us substantively is that older children in general less frequently have neglect allegations on their files than do younger children in this data. But that 0.06 is incredibly difficult to interpret on its own. It's a change in the log odds. What people will often do is exponentiate this number in order to turn it into an odds ratio. I recommend using the predict functions in R with the type equals response argument to convert it into a straight probability scale. That'll maximize, it'll minimize confusion generally. I really am not a fan of looking at regression tables like this. I think a visual often does a much better job here. So I'm going to use the dot whisker package to generate a quick dot and whisker plot that will visualize our regression point estimates for beta and the confidence intervals for beta. We've also provided a dotted line here, and this will tell us about statistical significance. If the confidence interval crosses the dotted line, the results is not statistically significant at conventional thresholds. If it doesn't, it is, and these are 95% intervals. So we can see pretty clear relationships across a number of the measures with the neglect allegations. And what this is telling us is that the average levels of neglect, the incidence of a neglect flag on this child's file differs meaningfully across these categories in the data, right? We're kind of not using a causal approach here. We're using a descriptive approach to regression here, but it works fairly well, and we're seeing a lot of patterns in the data. Next, I want to show you a Poisson model really quickly. So if we remember the aggregate data that we created, we have enter and exit here. And so what I want to ask is whether entries into foster care are related to exits from foster care. That is, do places with more exits have more entries? Do places with fewer exits have fewer entries? That would be assuming a positive relationship. Or, is there potentially a negative relationship? Does more exits mean fewer entries? That would be interesting. Let's take a look at it. We're going to estimate the model M2, and then I'm going to summary to take a look at it. And what we see pretty clearly is that places with more exits tend to also have more entries, perhaps unsurprising. We actually, what we're doing here is we're effectively, we haven't included any information about population size in the model, right? And so exits and entries are both going to be deeply influenced by the size of the underlying population. One way we can address that in a Poisson regression is with an offset. And what an offset does is that effectively, because of our log link function, if we take the log of some exposure variable like population size, because of the rules of logarithms, we effectively end up with a model where our outcome becomes entered over population. So that is, it becomes a rate model rather than a count model, which can be really useful to look at. And here we actually find something kind of interesting. After we adjust for population size, that is when we look at entries per population, we actually do see a small negative relationship. That is, we expect to see for every one new exit, negative 0.00005 fewer entries. So I don't know how far we want to take this. Again, I'm mostly estimating these models for us to learn how the software works. But it could be some interesting dynamics between entries and exits. We do know that, things like I think of the work of someone like Fred Wolksein, who's shown some really clear relationships between the capacity of a system and the number of entries that are generated within the system. Okay. And I did call LME4 at the appropriate time. If we don't have, now we're going to pivot to multi-level models. If you don't have LME4 installed, you can just run this install.packages line to install it. We don't need to do that more than once, though, for each installation of R. So we can just run the library in there. I want to go ahead and set up stnum in AFGAR's end. If we go back up, AFGAR's end includes a, where is it? It's actually not showing up on my screen output, but there is a variable. Oh, no, there it is, stnum. This is a unique identifier for a state. It's a state FIPS code. And it looks like numeric right now, but I want to make sure that R handles this as a categorical variable, not as a numeric variable. So I'm going to force it into a factor. So we'll use mutate to force that state identifier into a factor. And I'm going to compute entry rates per 1,000 population as entered over pop times 1,000, exits per 1,000 population as exits over pop times 1,000. And we're also going to center our year measure. When we're estimating multi-level models, the estimation can get fairly complex. And when we have measures on very different scales, like our entry and exits per 1,000 are going to roughly be on a 0 to 10 scale. But then if we throw year in there, which has a scale in our data from 2015 to 2019, it's on a really, really different register. So we're just going to center it at 0 by subtracting off, well, not quite centering it, but we're going to do a linear transform of it to make it begin at 0. So it's on a similar scale to our entry to exit measure. Another approach to this that we can use is to use a scale transformation using the scale function, which will just do a mean-centered Z transform. That is, it'll subtract off the mean from a vector and divide it by its standard deviation to turn everything into Z scores. And if you ever run into convergence issues with multi-level models, or if you estimate Bayesian models, those Z transformations can be incredibly helpful for improving model convergence. They don't change the relationships in the data, but they do change how the parameters look. All right. So we're going to estimate our first model, M4ML, right here. We're going to use Lemur to estimate entries per 1,000 as a function of exits per 1,000, plus a random intercept for each state and a random intercept for each year. This is typically how I like to handle time variation. Rather than assuming a linear relationship between time and the outcome, instead, we can use intercepts to flexibly fit whatever is going on over time. We don't need to impose any kind of assumption that it must be increasing or decreasing in a consistent way over time. Instead, we're just going to use the data to estimate an intercept specific to each year and allow that to vary flexibly over time. Let's take a quick look at this output. So what do we have here? We have some new components. First, we can see as before that we do see a clear relationship between exits and entries, significant at conventional thresholds. But we have a whole new component to our output now. We have this random effects portion of our table. And what this tells us is the variance of each of our random effects components. So now we have, at a glance, we know that we still, after including everything that we've included in the model, we have a 0.52 residual standard deviation, but our state intercepts have accounted for quite a lot of variation, as have our time intercepts. we can think about this as how much, after we adjust for time stable differences across states and national differences over time, how much variation is there still remaining among state year observations? And still quite a lot, but our multi-level structure of our model has accounted for quite a lot of extra variation that we didn't account for in the non-multi-level version of a model like this. Finally, we'll estimate a model that includes random slopes. So now we've changed our specification of our random effect structure a little bit. Instead of having an intercept for each year, now I'm going to have an intercept for each state and a slope for each state that's a function of time, right? So that is, each state will have effectively a linear growth trajectory, its own linear growth trajectory. We've included year C here as a predictor in the main model to estimate a national linear growth trajectory, so that then these individual state slopes can be interpreted as deviations from the national trend. So let's estimate that and take a look at what we get. All right, so we can see here, anytime I see a standard deviation that's meaningfully non-zero, it's telling me that that is accounting for some patterns in the data. So in this case, we're seeing that we estimate substantial variation in these slopes across states. We still see substantial variation in the state level intercepts with some residual variation. This correlation here is telling us about the correlation between those estimated state intercepts and slopes. We're actually assuming a fairly complex variance structure in the relationships between these intercepts and slopes. And this is giving us a little bit of information about that. And we still see a similar relationship for exits. If we want, we can use goodness of fit comparisons to think about whether model 4 or model 5 is providing us with a better fit to the data. This might be a useful question if we're like, do we need slopes? Do we need intercepts? What kind of structure works best here? And in this case, we're seeing a substantial improvement in fit for our model with random slopes for each state. A BIC difference of 15 here is generally fairly meaningful. So in this case, I would say that model 5 is fitting the data better than model 4. And if I were using model fit as my primary criteria for selection, I'd probably prefer model 5 at this point. So that's all I have for today.
Thanks, Frank.
The National Data Archive on Child Abuse and Neglect is a joint project of Duke University, Cornell University, University of California, San Francisco, and Mathematica. Funding for NDACAN is provided by the Children's Bureau, an office of the Administration for Children and Families.